Boltzmann transport equation. So Boltzmann transport equation is mainly when Boltzmann derived it or proposed this equation, it was completely classical. So at that time, so this is classical mechanics. So at that time, classical mechanics was so classical mechanics started with Newton's law. So that was Newton's formulation of classical mechanics. Then it get developed, and there was this Lagrangian formalism and Hamiltonian formalism. So this was by Lagrange, and this is by Hamilton. So this is Hamiltonian formalism. So this is same classical mechanics, but in different ways. So what is Hamiltonian formalism? So uh, we talked about this Hamiltonian in Schrodinger equation, but it's actually started with a new way of thinking classical mechanics. So Hamiltonian is you can think of as energy function of position and momentum. So there is a so in Newton's law we all know about x, which is position, or in vector notation x vector, and velocity v is dx by dt, and momentum p is mv. That is the usual momentum. But in Lagrangian formalism, there is something called Lagrangian, which is function of x and this v, which is written as x dot, and from there you can calculate momentum by taking the derivative of the Lagrangian with respect to x. So, for example, in Lagrangian formalism, basically it is kind of the kinetic energy minus the potential energy, which is half m. So this is with respect to t, half m v square minus the potential energy, which will depend on x. And if you take the derivative of L with respect to v, so you will get basically mv from this term, and this is independent of v. Okay. So this is the kind of the general definition of momentum, which is derivative of L with respect to t, and v is nothing but the time derivative of x. And then Hamiltonian mechanism is formed in terms of the Hamiltonian, which is related to the Lagrangian by a simple formula. So this is the Hamiltonian is Lagrangian minus p dot v. So this is p dot v minus the Lagrangian. Hamiltonian is p dot v minus the Lagrangian. So basically, this is known as the Legendre transformation. And if you take that, then Hamiltonian will be p dot v minus the Lagrangian, and Lagrangian is nothing but so b is now b is p by m. So everything in terms of p by m is p square by m minus this is p square by 2m plus v of x, which becomes p square by 2m plus v of x, which is the total energy, kinetic energy plus potential energy. So this was actually the kind of formalism in classical mechanics. So Hamiltonian is a function of x and p, where x is called x and p are called conjugate variable. So this was kind of the formalism at that time, and the Hamiltonian mechanics is given by how the x and p will vary. And the Hamiltonian mechanics is the rate of change of P, which is also written as P dot, is given by the derivative minus the derivative of the Hamiltonian with respect to x, and rate of change of x, which is given as x dot, the rate of change of x will be plus the derivative of the Hamiltonian with respect to p. So this will give nothing but give you the classical laws of classical law, Newtonian laws for this Hamiltonian. Because if we take this Hamiltonian, then we can easily see that the Hamiltonian dH dx is, this term is independent of x. This is only depend on p and x are independent variable kind of thing, and v of x will give dv by dx. So the first term will be the rate of change of momentum is minus dv by dx, which is nothing but the force. V is the potential energy. So this is the Newton's second law. And what dh of del h of del p gives, it gives p by m basically. So this gives that x dot dx dt, which is nothing but the velocity, is p by m. So p equal to mb. What is the momentum? So basically, these are nothing but Newton's law. So this Hamiltonian mechanism and this relation, that dx dt will be minus del h del p. Dh dt will be plus del h del p, and dx dp dt will be minus del h del x. This is known as the Hamilton's the equation of motion in the Hamiltonian formalism. Now, not only how x and p changes, let's say any function of x and p, that can be any function, that can be how energy is nothing but the Hamiltonian, but angular momentum could another thing, and uh, so on. So basically, any function of xp, which let's say f of x and p, then it can also explicitly depend on t. So how this function will change with time, and that will give you how, if you measure some properties like angular momentum, let's say, then how angular momentum is changing with time, because the system is already given by this variable. I mean, yeah, if you have some many particles, then there will be many such variable, but this is the same equation. So basically, then you will get that the total rate of change of p is nothing but these simple things. I'm just using the chain rule of derivative, and then I'm applying this Hamilton equation of motion. This is the equation of motion, and if I apply the equation of motion, the first term I get df del x plus del h del p, and the second term df dp, and there's a minus sign because of a minus sign here, dh dx plus df dt. And this quantity appears in all the time, and they have defined this quantity as the Poisson bracket of f and h plus df dt. This Poisson bracket is nothing but the definition. So there are f and h, both are function of this is also a function of x and p, this is also a function of x and p basically. And in classical mechanics, this Poisson bracket is defined as taking the derivative in first this order, then taking the derivative in the opposite order. And so this one becomes the commutator in quantum mechanics. And so this equation df dt equal to f comma h plus df del f del t. And this is how any function, any observable will change with time. And this Hamiltonian, the system is described by this Hamiltonian system description by this Hamiltonian. But how any observable or any measurement observable uh, will move, observable behavior of the observable with time is given by this equation of motion. And this one actually goes into the quantum mechanics by so-called Dirac's correspondence principle. And what happens in quantum mechanics, this f becomes an operator. So how the operator will change will become these things: 1 by I h bar, the commutator between the operator and the Hamiltonian operator, plus if there is any expressive time dependence. And here this is operator, Hermitian operator. Because this is an observable, this is the Hamiltonian again. Hamiltonian now operated, and since f is observable, so this is an Hermitian operator. But yeah, so now the thing is, the what is the correspondence principle? The correspondence principle is whenever there is a commutator between two things, that will should be replaced by 1 by I h bar this one. And why is it so? Because if we try to calculate the commutator between x and p, simple one variable, so it will be del x del p minus uh, del x del p del x. So what is del x del x? Del x is 1, del p is 1, and what is del x del p? They are independent variable. X and p are independent variable. So this is 0 and 0. So entire thing is 1. So in classical mechanics, the Poisson bracket between x and p is 1. In quantum mechanics, x and p is I h bar. So, and also in Heisenberg, so the Heisenberg equation of motion, and this is the Heisenberg equation of motion, where the operator changes with time, Heisenberg equation of motion. So Heisenberg derived this equation of motion differently, but then Dirac proposed this correspondence principle. Okay, so any question? So this is Heisenberg equation of motion. And what is Heisenberg equation of motion? So uh, actually I told quantum mechanics in point of view from Schrodinger. So Schrodinger equation, sorry, Schrodinger equation was how the how state changes with time. And we have this Hamiltonian operator H, which acting on a state, and I am writing the state in terms of Dirac notation, bracket notation, is I H bar, and how it changes with time is given by this equation. So I am using Dirac bracket notation, and this state psi of t is changing with time, and it started with some t equal to 0. It started with some state, let's say called phi 0. So this is the initial condition, and this is how the state changes with time. That is Schrodinger equation. That is what Schrodinger said. Now Heisenberg proposed a different kind of view, which is the state psi doesn't change with time, doesn't change with time, but the operator may, but any observable may change. Observable changes with time. May change with time because Hamiltonian may not change with time, change with time. So now if Hamiltonian, so this is the symmetry, if Hamiltonian operator is time independent, then there will be conservation of energy. And that is the idea behind the stationary states, where you are only solving for the time independence or linear equation, basically after that. Now, Heisenberg proposes how the observable will change and what we measure. The question is what we measure. The question, so in Schrodinger equation or Schrodinger picture, we measure any observable with respect to a wave function psi. So this is psi of t and observable and psi of t. This is what we kind of measure. And the psi of t is given by a unitary time evolution operator, which is minus I h t by h bar psi of 0. This is a unitary time evolution operator. Let's consider h does not depend on t, so that's why h is independent of t. And then we measure this thing basically and the complex conjugate, and that can be written as psi of 0 e to the power I h t o e to the power minus I h t psi of 0. So what I have done, I have explicitly broken psi of t equal to e to the power minus I h t by h bar psi of 0 here and taken the complex conjugate on the other side and O operator in between. This is the complex conjugate. So that becomes the plus I h bar. And then I can think this as taking the expectation of this new operator with respect to the old state. So in this picture, uh, the state psi of 0 doesn't change, but this operator changes e to the power I h t o at t equal to 0 e to the power minus I h t by h bar. So this kind of evolution of the operator, again, I am just giving you a kind of justification when h does not depend on time. So this is the kind of justification when h does not depend on time. Can we? So it's like we can move the time dependence to the operator, and that is called the Heisenberg picture. But yeah, so but again, you can derive this equation in the Heisenberg picture for any observable and how it will changes with time by this formalism by this okay, you can derive that this equation using this formalism like psi doesn't change with time, or what changes with time is only the operator. So basically this, that's why this there is this correspondence principle. So why I am telling you this, because now I am going to move to the Boltzmann transport equation. And the Boltzmann transport equation and correction of Boltzmann transport equation, a quantum mechanical correction. So the first thing is Boltzmann transport equation. And the second thing is quantum mechanical correction. And Spinor Boltzmann transport equation and so on. So we are going to use these two ideas, that how the any function changes. So in Heisenberg picture, let me write it down again. Any observable O changes by this equation. This is Heisenberg equation of motion. So now let me go to uh, Boltzmann transport equation. So now in class Hamiltonian mechanics, particles. So let's consider only one-dimensional case. This is x and p. There are two variables. So the motion of the particle is is calculated, or the motion of the particle is actually tabulated. Say particle is moving by noticing the position and the momentum x and p at each point of time. So this is how a particle is moving. And if this is the same, there are many particles. Particle will move by kind of the same law, which is the Hamiltonian h, and the motion is dx dt is equal to plus is equal to del h del p, and dp dt is equal to minus del h del x. This is the equation of motion. Now, if there are many particles, this will satisfy for each particle. So, there will be a I. There is not I uh, component. So, this is for particle one. I goes from 1 to n, and again n means 10 to the power 23 number of particles, kind of thing. This is equal to n. So there are so many particles. So there are many particles, and all the particles are moving by this equation of motion, which is the Hamilton's equation of motion. Now we cannot. So this is impossible to track all the particles because there are 20 over 23 number of particles. There might be interaction between them, and this Hamiltonian is function of all these particle xi and all of their momentum pi. So this is a So if there are n particles, if there are n particles, so we have a 6 n dimensional phase space. I have just written, I have just drawn the one dimension, but there are actually 3 dimensions. So 3 n positions and 3 n momentum. So 6 n dimensional phase space, 6 n dimensional phase space. So and this is called the phase space. So the idea, and it was, I think, it started with Gibbs. It was a Gibbs idea also, and also Boltzmann has this idea that we are not going to uh, calculate the momentum and position of everything, but we will. So this is kind of many particles. So we will define a distribution function. So this is so define a probability distribution function. F, which depends on all this xi, pi, and also on time, how it changes with time. And this probability distribution function tells you what is the probability of finding the particle. Again, what distribution function tells what the probability of finding the particle in xi and xi plus dxi and pi plus dpi. So basically, if you take a point and in the neighborhood of the point, what is the probability of finding the particle uh, in that point, and in a small volume, dxi dpi, this is the small volume. This is the probability distribution function, and it must be normalized. So the normalization is uh, the normalization is so what is the number of particles? F gives you the number of particles finding. So the normalization is this is this f, which depends on all this position and momentum, and you are doing integration over all the xi and pi coordinates, all of them, and you should get instead of one, it's like a kind of n. There are n number of particles, so you should kind of get n. Uh, this is a kind of normalization. Now, again, uh, what should be the equation of motion for this all these particles? So let's not consider all the particles. Let's consider we have only one particle, and one particle is moving somehow, and we are actually giving it some kind of a distribution function f. So how the distribution function of f will move? So f is kind of probability distribution function, and the probability is conserved. And the probability is conserved means it's f must satisfy some kind of continuity equation. And I'm only considering one variable x and p, x and corresponding p. Is if f satisfy continuity equation, so that means the rate of change of f with time plus the so gradient of, so in 3D will be gradient of the current. Current means velocity times f. So if I have a particle and it has some velocity v, and the part, so let's draw this picture in x. So I cannot draw more than 2 because I cannot draw 4 dimensions. So just think that it has some velocity, and this velocity component, this velocity is not velocity dx dt, but velocity in the phase space. So this is the velocity Vp, let's call Vp in the phase space. What is the phase space velocity? So this is the phase space velocity. So think that if this is not p, this is a y coordinate and a particle is moving, then the particle will have some velocity. So just if p is a y coordinate, so that will be the velocity. There are 3 plus 3 equal to 6 coordinate for only one single particle. For many particles, there are even many coordinates. So uh, this is the velocity, and what is, so this is the rate of change of density. So in the continuity equation, a continuity equation looks like this: del rho del t plus del dot j is equal to 0. And what is j? J is kind of n times, uh, if this is the electric, this is electric current, then you will multiply by E. Otherwise, this is n times V. So, otherwise, J is n EV or n times V. So this is kind of the idea. So the continuity equation, if the F will satisfy continuity equation, this will be 0. And this velocity V is nothing but the space velocity. And from there, uh, the idea is that if this is true, then we'll get, and this is also acting on phase space. So this is a phase space velocity. And this gradient is also acting on the phase space, which acts on the x as well as the p coordinate. So if you do the mathematics, so this is like uh, gradient acting del r acting on this velocity v f plus del p acting on this velocity v f is equal to 0. So if you do the mathematics, then you will see that it can act on the velocity at or it can act on the function. So you will get 6 terms. So one thing is del r acting on function, and the velocity v will be out. And in this case, since r will act on v, so velocity means it will be just dr dt, plus similarly same term from here vp means, so this is I am denoting by vr, and this is the vp component, r and p component. So this is the phase space velocity. And similarly from there you will get a dp dt dot del p of f, and the extra term which is remains is f of ddr of dr dt plus ddt of dp dt. But dr dt is del h del p and dp dt is minus del h del r, which is nothing but the equation of motion in the. So this is very important. You need this equation of motion for deriving this equation. So this term goes to 0, and what you are left to it is just del f del t plus this thing dr dt del r or f plus dp dt dp dt del p of f is 0. So this is called the Liouville's equation, and the idea again is that the phase space volume cannot change. So this is same statement as the phase space volume in classical mechanics cannot change. The phase space volume cannot change. So that's the idea. And then the Boltzmann transport equation. So the Boltzmann transport equation is so this is for one particle I have shown you, but for n particle also you will get the same equation. The Boltzmann transport equation we write is like in this form: del f del t plus dr dt dot del r f plus dp dt dot del pf is equal to some collision term, and that is written as a function of f, which is a collision term. And this collision term in the relaxation time approximation is some f equilibrium by tau. So this is in the relaxation time approximation, and this is in general collision term. And the idea of collision term is the collision actually changes the phase space. So if this particle is moving and then getting collided by other particle and so on, so it is actually changing the phase space distribution. So basically it's actually if you start from here, so it's actually a source term here. So you change this right hand side by a collision term. So collision term is actually a source term. So if you have a continuity equation, so you will change the right hand side by a source term. So similar idea here, if you change the right hand side by a source term kind of thing, source or sink term, which is due to the collision. So the collision changes the distribution function. So the idea is the collision changes f. Change, I mean, of course, changes f means it can, so it will not change the, so the collision will be, but one thing is important, that we need the continuity of particle, so the particle number must be conserved. So collision will not change the particle number, uh, but it may change the energy and the momentum and other things. So it may break many symmetries, and that's why there is called relaxation, which will lead to relaxation of momentum, or momentum relaxation and energy relaxation and so on. They are all those things. So it changes the it breaks the symmetry, and actually, so that is the picture. And from here to here, what we have done is we have had this 6n-dimensional space, and the actual procedure from going from here to here in classical mechanics is known as the BBG-KY hierarchy. The BBG-KY hierarchy is named after Bond, Bogoliubov, Green, Kirkwood, and Eve. The idea of BBG-KY hierarchy is We will not directly grow. So we have a distribution function which is for n particles. So a distribution function in the space, a distribution, we have a distribution function and we're following all the n particles, n particle distribution function, but we can define all this n minus 1 particle distribution function by integrating over one coordinate of this n particle distribution function. Then n minus 2 particle distribution function by integrating another coordinate dp n minus 1 of this n minus 1 distribution function, which is nothing but integrating two coordinates in the n particle distribution function. So what does integration means? Integration means we are blurring out thing. We are taking the average. So we are taking two. We are integrating over two coordinates. So we have reduced the number of two coordinates. So in this way, we can go down to two particle distribution function and the one particle distribution function. The two particle and one particle distribution function will be integrating all the coordinates except the first coordinate of fn. So it will give a function which will be dependent on the first coordinate only, for only one particle, and then this distribution function will satisfy equation uh, which is called the Boltzmann transport equation. Basically, this distribution function will satisfy Boltzmann transport equation. But again, if you derive all these things, because if fn satisfies this Liouville's equation, and the Liouville's equation is this equation, for n particle also the same thing. And then if you write down all this hierarchy, then all the equations will still satisfy, is coming from the same equation, Liouville's equation. So you are not gaining anything. So 6n dimensional, like n particles, and you are writing down n distribution function, you are not gaining anything. So while writing down this distribution function, there has to be some approximation in the Boltzmann transport equation, and that approximation again comes in terms of this collision term or particle collision term, basically. So this collision term is kind of ad hoc, but that is the essence, and you have to use this collision term in Boltzmann transport equation. Otherwise, you are again dealing with the same in particles, large number of particles. So this approximation is always there. And the idea behind Boltzmann transport equation is, I told you about the equilibrium distribution function. And I derived the equilibrium distribution function from maximum entropy principle. So derived from maximum entropy principle. And then when Boltzmann's, so in Boltzmann, so maximum entropy principle means entropy will always increase. Now the question is how equilibrium is reached. So how do you get to the equilibrium? How do one reach the equilibrium? And that's why Boltzmann derived this equation, and this is the distribution. And by this one, if, I mean, this distribution will tell how the equilibrium is reached. So that is, so the time evolution of the distribution function and relaxation time approximation. This is this f minus f equilibrium. So this is the relaxation time approximation, but without relaxation time approximation, there will be I of collision terms out. So this equation will tell the evolution of f and how the evolution of f and how the equilibrium is reached. So there must be some quantity which will, so if there is a entropy, there must be some quantity, must be a function which only increases with time. Then only you can satisfy this that entropy always increase, the second law of thermodynamics can be satisfied. This is the second law of thermodynamics. Can only be satisfied if there is a function which only increase with time, or a function which only decrease with time, only decrease with time. And then I gave you the idea of entropy from the ensemble picture, that S is kb log of number of uh, ensemble. So this was the formula kind of thing. But here we have a distribution function, and there is what is the meaning of ensemble. So what is the meaning of distribution function? So uniform distribution is something like 1 over some number capital N. This is not the particle number, but some number. This is the idea. I am just talking about the idea. What is a uniform distribution? The uniform distribution is so if you have a dice, then all the six faces has equal probability. So the uniform distribution is 1 by 6 probability for each face. So this is kind of the uniform distribution, and this is kind of the uniform distribution. So S is in that case would be k log of this capital A. Capital is the number of states, and we can write this as minus kb uh, log of 1 by n. Okay, so that was the idea. But again, if it was a uniform distribution, but if the distribution of is not uniform, we have to take some kind of average. So there is this Boltzmann H function, and let me again call it H of t. H of t was nothing but this integral over all the positions and this space. So you are taking kind of a average of log of f. So this is for average. So uh, this is the idea of averaging. This is averaging. This idea of averaging, like if I have this distribution function f, r, p, and t, so there are different definitions. So one is the density. So density is averaging over all the momentum. So density n of rt is averaging over the momentum component of this function. Similarly, the concept of current, which also depends on RT, is averaging over the momentum times the velocity and times the function. So basically this is average over velocity. So this is the concept. So this, since this depends on R, so that is the concept that you are only averaging over the momentum space. But again, this nRT must satisfy that nr of t times d cube r must be the total number of particle n. So n is d cube r d cube p f of r p. So that's the kind of the concept of averaging, and we have this kb, the Boltzmann's constant. You can multiply it by Boltzmann's constant, and the idea is this log function, so which is nothing but kind of the uh, average of the log function kb, and kind of a statistical average of this function log of it. And the idea was, then Boltzmann had shown that if I have a collision term if, so we need to first find out what collision term should we use. So the collision in classical mechanics is like, so this is the collision. So I have colliding a particle with momentum p1 with a particle with momentum p2. They are becoming p1 prime, p2 prime. This is some collision center. So the probability of particle was p1, probability was p2, and after collision it was p1 prime and p2 prime. So the collision term is some kind of this term which is the incoming. What is the probability of incoming rate is multiplied f of p1 times f of p2 minus the outgoing rate is f of p1 prime f of p2 prime. So this is one kind of collision term, but again I have just gave you the expression of the collision term, but again that was justified by some means starting from this BBG KY hierarchy. And with this collision term, that Boltzmann has showed that H dH by dt is always less than equal to 0. And this H is not the Hamiltonian, this is the Boltzmann H function. This H is always decreasing, and so if you define S as minus KB and log of F with this averaging thing, then this S is the entropy, and entropy dS by dt is always greater than equal to 0, and entropy is always increasing, even strictly greater than 0. So that was the Boltzmann H theorem. That indeed, this Boltzmann transport equation uh, gives us a process which establishes the equilibrium. So that was the idea, that this Boltzmann transport equation describes a process and establishes equilibrium after some time. And when the equilibrium will be established, when this collision term actually becomes identically equal to 0, so the collision term, which means the collision no more changes the collision no more changes the distribution f, statistically speaking. So the distribution overall remains the same, and again when the collision term will be 0, so you will have f of p1, f of p2 will be equal to f of p1 prime, f of p2 prime, and if you take the logarithm on both sides, then you see that logarithm of this function p1 plus p log of p2 is collision invariant. Collision invariant means it remains the same even after the collision. So this is before the collision, and again after the collision it is the same thing, p1 prime plus log of p2 prime after the collision. So if log of p1 plus log of p2 is collision invariant, so we know that there are some conservation. So first of all, this I of f actually conserves certain things. So like energy, momentum, and all this conservation must be true, and there will be a rate, let W, let's call it, which will be multiplied by this function, and W will be such that all this conservation, energy, and momentum are satisfied, because this is a collision, classical collision, and let's say classical collision, all these conditions are satisfied. Then this is a two-body collision again. Then this conservation of momentum and energy tells us that if log of P1, this log of P1 is some constant alpha, some constant beta dot P, and some constant of E. So it's not written like that. It's written some constant E naught of P and some constant beta times E. So if log of P on 1 is in this form, then P is a collision, P is a conserved quantity, energy is a conserved quantity, momentum is a conserved quantity, alpha is a constant. So log of P1 is also a conserved quantity, and that will give log of f of P1. This is f, log of f of P2, log of f of P1 prime, log of f of P2 prime. So log of f of P1 is a conserved quantity. So you get log of f of P1, f of p is some form alpha plus beta e plus v naught v dot p, and you can choose the sign also. So I'm just giving you a ideas. Then f of p, the distribution function at equilibrium, will be in the form e to the power minus alpha, e to the power plus alpha, e to the power minus beta e, and e to the power v dot p. So this is actually will give the so-called Maxwell-Boltzmann distribution, and this beta will be nothing but this 1 by kb. So the idea is that the Boltzmann transport equation at equilibrium also gives you the Maxwell-Boltzmann distribution. And if you just, for quantum mechanics, if you just include Pauli exclusion principle, and then again you will change the collision term. So I of f, now you have a Pauli exclusion principle and two body collision. So whatever electron is coming is going. Something is happening, and there is Pauli exclusion principle and indistinguishability. So I cannot exactly draw what is. I cannot label the particle, but this collision will be proportional to this incoming and outgoing electrons, whatever the set. This is the collision rate, and this collision rate will be given by Fermi-Golden rule, and I'll talk about Fermi-Golden rule after this. So this is the collision rate, and the main part is the distribution. So the collision will happen depending on P1, P2, but this is the probability of occupation for P1 and probability of occupation what was occupied P2, but it cannot get collided, so it cannot occupy the same state again. So it must be also 1 minus fp1 and 1 minus fp2, because it cannot go to the same state p1, that is prohibited by Pauli exclusion principle. So that incoming rate must be adjusted such that this is satisfied, and so the outgoing rate. So this is 1 minus f p1 prime, f p2 prime, and f p1 prime, f p2 prime, 1 minus fp1, 1 minus fp2. And again, yeah, at equilibrium, if I of f is 0, that gives this entire quantity is a collision invariant. So if you take the logarithm, so logarithm of f of p1, so this so before that, f of p1 times f of p2, 1 minus f of p1 time, prime, and 1 minus f of p2 prime is equal to uh, f of p2 p1 prime, f of p2 prime, and these terms 1 minus f of p1 and 1 minus f of p2. So this is the collision from in state and out state, but the collision can also be other way around. So we have to consider all those things, and there will be also summation over all the momentum p prime. But again, each term will be 0, and that is also known as the detailed balance. So now these two things will be 0. Now if you divide this by this times this on the both side of the equation, then if you get f of p1 by 1 minus f of p1, and the similar term for f of p2 is conserved. And if you take logarithm, log of this plus log of that is conserved. And again, which means just by the previous, just what happens previously, the log of f of p1 must be of this form. So if only energy is conserved, also momentum can be, so energy is conserved. So then you will get f of p1 by 1 minus f of p1 logarithm be some alpha minus beta e, which will give f of p1 by 1 minus f of p1 is equal to exponential alpha exponential minus beta e, and that will give the Fermi-Dirac distribution. If you just do it, you will find that that will give the Fermi-Dirac distribution. So again, the idea is that Boltzmann transport from the Boltzmann transport equation, the distribution function actually gives you how the equilibrium is reached, and there is a Boltzmann H theorem which tells you that indeed this Boltzmann transport equation shows how things changes with time, and there it also satisfies the uh, maximum entropy principle of second law of thermodynamics. Maximum entropy principle. This also gives you the thermodynamic properties and things like that. But again, there is the approximation by which these collision terms are derived. Otherwise, there will be no Boltzmann transport equation. So the idea is, even though the laws of physics are deterministic, there is some kind of averaging is happening, or coarse graining, or we are not looking at all the degrees of freedom. We are only looking at average properties of matters and average properties of things. That's why there is some loss of information, and that's why that's the concept of entropy and everything. So I'll take a break here, and then next I'll talk about the Fermi golden rule. So any question till now? Any question from the audience?
Hello. Uh,
Hello, hi,
Good morning, sir.
good morning.
Sir, as we are teaching students classical mechanics to the PG students.
Yeah.
So now, as per the new education policy,
Hmm.
uh, they are asking for experiential learning. So when student will learn these topics,
A-
so what is the
a-
experiential learning of these subjects?
Asking for what?
Experiential learning.
Experience learning.
Uh, why they're learning these topics?
Okay, okay, okay. So the classical mechanics at least, right?
Yes,
Okay, so yeah, let me tell you that. The point of learning classical mechanics for physics students maybe uh, uh, so there so yeah, so classical mechanics, so there are two ways that the classical mechanics can be taught. So basically one is this most of it can be taught in very uh, the historical way, I should say, and not historical way, like how it was developed and how were modeled, experimental modeling and things like that. And then experiment was modeled by different laws. And then the another one is a very theoretical way. And the theoretical way of learning classical mechanics is let me first. So this is like teaching the very basics of. So I have to mute some of you because there are some disturbances. And theoretical way is learning from this principle of least action, and the classical particle mechanics, wave particle mechanics, classical field theory, and everything from Lagrangian and Hamiltonian point of view. So those who are doing research in the theoretical physics part, uh, and right now the actual research in the theoretical physics part are divided into main branches, which one is condensed matter, another one is high energy. So for high energy, this has a direct relevance, because for high energy and theoretical research is mainly on string theory and quantum gravity and other things. For that part, this is highly relevant, because that's the basic backbone or basic building block of every theory. So that is one way why one should learn very deep theoretical way, like Lagrangian, Hamiltonian mechanics, and so on. For condensed matter theories, also nowadays, so this Lagrangian and Hamiltonian mechanics are used actually in many places. So so if you want to come up with a theory, so right now in condensed matter, the actual theory, in research of condensed matter in actual theory, so there are this idea from high energy that are coming into the condensed matter. Like one idea is Chern-Simons theory to describe topological phases. So there basically everything is described in terms of this Lagrangian and Hamiltonian kind of the basic theory. And then Hamiltonian is very important, because Hamiltonian, so because all the quantum mechanics formulation is based on this Hamiltonian theory. So if so that is very specific actually. I mean, this theory are not very doesn't have any kind of direct practical application of learning these things, but only is useful to those who are doing research in pure theory. And uh, this experimental model, why should we learn all the classical mechanics like Newton's law? So these are all everywhere, like in optics, in mechanical system design, and so even if you want to, so in different equipments, uh, so whoever is doing experimental physics, this is very relevant. I mean, at least from this point of view, that you should know all the laws of the classical mechanics and how you model all the experiment. And this is very important, because whenever you are doing some experiment, you are either so at one point of time or another, so you are going to use all this kind of theory, uh, more or less. So all the theory from like classical, all the classical mechanics, classical statistical mechanics, and classical electromagnetism. So this is very relevant. I mean, of course, doing some quantum mechanics experiment and things like that. Uh, but even if you are doing some quantum mechanics experiment, things like that, but when you are dealing with the overall experimental procedure, then there will be many classical effects that you should know beforehand, so that and that. in many times when you have to calibrate the equipment, calibrate the measurement and things like that. So this is very useful actually. So at least from experimental point of view, I think knowing, not going into the details of this Lagrangian Hamiltonian mechanics, but at least knowing the laws of classical physics is important. Experimental learning is learning by doing, but thing is you should need to know at least the basic theory and how you will model some kind of experimental data, or how will you know that whatever you are modeling, what theory you should use and things like that. So I am only talking about, I am not talking about just learning by doing. What I am talking about, when there will be some problem, whenever you are doing some experiment. So if the experiment goes smooth, then okay, you will learn by. But there, in many times, you will face with some problems in the experiment, and you have to resolve that problem. And when you have to resolve that problem, then you have to use some understanding from your theoretical background, and at that time, it's very needed. Otherwise, not. I mean, yeah.
Okay, sir.
So
Thank you,
that
sir.
is what I felt. I mean, when I did a experiment, that is what exactly I felt. Like I did experiment on molecular beam epitaxy, MB. I did a sputtering experiment, and uh, also I did many electrical measurement experiment. So basically, in many places it was very much needed, like uh, to use concept from basic laws, like classical mechanical laws, classical mechanical theories and things like that. And not only while doing the experiment, designing the experiment, but sometimes when I got some results which is unexpected, then I had to resolve that, and then I found out, okay, this is the origin of the outcome and things like that. Okay. Any other question? I hope that I have answered your question.
Yes, sir.
Yeah, yeah. Okay, so any other question? Okay, then I'll. So this is the last topic for this session. I'll talk about the Fermi Golden Rule, and Fermi Golden Rule is very important because uh, uh, this Boltzmann transport equation is nowadays used in everywhere. It is not limited to classical mechanics. So and Fermi Golden rule mainly comes into the collision integral of Boltzmann transport equation. To calculate the collision integral of Boltzmann transport equation, Fermi Golden rules are used. So collision integral in Boltzmann transport equation, and the collision integral term is, you have this term dfdt, drdt del r of f plus dp dt del r of p del p of f is equal to this collision integral. And collision integral is nothing but you have to, so this is actually kind of modeling. We have to model what collision integral should be, and this is actually sometimes given by the Fermi's golden rule and the rate from the Fermi golden rule. And so I'll just further us briefly describe the original idea behind the Fermi golden rule, which is quantum mechanical idea. So again, Boltzmann transport equation, the application of Boltzmann transport equation in everywhere is not limited to classical mechanics or semi-classical mechanics. Is everywhere basically, and in quantum mechanics also, in quantum mechanical systems also, to describe uh, quantum mechanical systems. And Fermi golden rule, similarly, the application of Fermi golden rule is also widespread, and it's not only limited to the original quantum mechanical perturbation theory idea. So I'll first describe how what is Fermi golden rule. So I was talking about this time Hamiltonian age. Uh, so this Hamiltonian operator acting on psi gives it should be plus I h bar beside it. Now, uh, the first day I started with this psi, and I told that h is minus h square by 2m del square plus v, and I told that v could be r, v could be r and t time dependent also. So there could be a time dependent potential, and then I said that if is time independent, if v is time independent, then we will have stationary state solution. Stationary states, and that will be given by h psi of n equal to en psi of n. Then we will have eigenfunctions, eigenvalues, and eigenfunctions, values and functions. So that will give you all the stationary states starting from the bottom towards up, so and so. So n equal to 1 to discrete state, or it might be continuous also at the some point, and so on. So now, what happens if h is time dependent? The question is, let's say h is time dependent, or the potential itself is time dependent. V is not time independent, it's time dependent. Then we divide this h actually in two parts, h naught plus h prime, and this h prime is the time independent part. H prime is the time independent part, and h naught is the time independent part, and h prime is the only time dependent part. So, like if the Hamiltonian has some another potential V naught, which is so not less than V naught, write down here. So basically, I am writing V uh, R and T is V naught plus V prime, which only depends on T. And this can also depends on R, but yeah, in these two form, and then H naught, then H naught is nothing but the original one without the time dependent part, and then h prime of t is nothing but this v prime of t. Now we know how to solve this part, and this v prime of t is the only perturbation. So I can also write it down h naught plus v prime of t, and this is the perturbation. So the idea here is uh, we have calculated all the eigenstate. So h naught with h naught we have solved this equation. H naught of psi is equal to uh, psi of n is equal to En psi of n. This is the time independent Schrodinger equation, and time independent Schrodinger equation gives us all the eigenstates and eigenfunctions. But since actually Hamiltonian is time dependent, so the idea is we slowly turn on p. So at time at t less than 0, this Hamiltonian is h naught. Then we slowly kind of turn on, and it becomes at some point uh, t on, it becomes h naught plus h prime, and this is basically I'm turning on there is a knob, and by switching on the knob, I'm going from h naught to h naught plus h prime. So when I was at h naught, then there was this eigenstates, but at once the Hamiltonian changes, so eigenstate means if a particle at a particular state, let's say initial state I, it will remain there forever. Now since the h naught changes, so if the particle started with this particular state I, it will not remain there, but it will try to switch to other states also, and there will be a particular probability of going to the other state, and we are going to calculate that. And this is mathematically written like this. So this is the idea. As switching on the Hamiltonian, we will get a finite transition. This is transition from one state to other. So uh, transition from state initial state I to all the other states k. Let's say k not equal to 1. So we are going to calculate that, and the idea is simple. So we know that the eigenstate psi n forms a complete basis, and we also know that if only h naught is present, so we also know that for only if only h naught, then what will be the psi of t? H naught and the initial state is I. So what will be the I is the initial condition. Then what will be the psi of t? Psi of t will be uh, uh, e to the power minus I en t by h bar n uh, n. Okay, the initial state, let me call it psi naught. Psi naught is the initial state where uh, psi naught is given by this n equal to 1 to infinity, let's say. So given a initial state psi naught, I know what these coefficients are. Coefficients are known because I have solved the equation h naught equal to psi n en psi n. Psi naught is my initial state, and if that is the case, then I know how psi t will evolve when the Hamiltonian is time independent. And this is the idea. So for time dependent case, this psi n, which psi n are still basis, because we can have a basis, and but the fact is psi n's are eigenfunctions of this Hamiltonian h naught. And the second part is we write down the psi of t. Psi of t will no more be e to the power minus I n t by h bar a n. Now we write down that at each time t there will be a different an, so an itself is a function of time. So we can think of it like at each time t, at each time t I will have a state, and I can write the state in terms of all the basis states, and because these science are basis, so this is n means science are basis. So in terms of the basis state, I can always write the actual state, and at each time if I do that, I'll get coefficients which is time dependent. And this is the idea, that we can always do that, and if we do that, then we want to find what or how a changes with time, a and t behaves, because a and 0 at t equal to 0 is still known given the initial function, any initial psi naught, just like before. So we want to calculate how a and t will changes varies, and that is the idea behind this time dependent perturbation theory. And this is done by taking so this is the original state. So the original Hamiltonian is h plus h naught plus h prime of t, and this original Hamiltonian acts on the psi of t, and that will be I h bar dt of psi of t. And the idea is to plug in psi of t, this entire expression here and this entire expression here, and see what happens. So if I plug the entire expression here, h naught will act on psi of n and give e of n. So I'll get e to the power minus I e of n t by h bar a of n of t, e of n. psi of n plus h prime will just act like multiplicatively. It's a potential v, and again e to the power minus I n t by h bar a of n of t of n. This is just operator. We can just write down that as an operator. The operator will act only on the state side, and on the right hand side, this time derivative either can act on this exponential or can act on this a or n of t. So if it acts on the exponential, I have I h bar already. So from here we will get minus I by h bar times plus I h bar, which is 1. So en to the power minus I n t by h bar a n of t psi of n plus uh, I h bar e to the power minus I n of t by h bar a n of t psi of n, and this time derivative acting on a n of t, and these two terms are the same. This gets cancelled, so we get an equation of a n of t. How can I get an equation of a n of t? Now we take a dot product with the k state k from the left hand side. So what we will get? We'll get summation psi k v, v prime psi n sum over all the n exponential of minus I e n t by h bar a n of t is equal to taking a product with k, and this is will be only psi k psi n, and these states are basis, means these states are orthonormal, and we will make this state orthonormal only also. So this is only one when k equal to n. So there I have I equal minus I equal to k t by h bar dA kt. So this gives an equation for a of k. dA of k dt is sum over all the others. So psi k v prime psi n e to the power, take that on the left hand side, it will be plus I ek minus en by h bar a n of t. And this is an exact equation. No approximation made up to this point. This equation is exact, and if I can calculate what ak are, given the initial an 0, initial an t 0 are known, then I can calculate exactly uh, the wave function. Now, this is the perturbative calculation, and the perturbative calculation is done by assuming. So, to start with, let's say initial ai of t equal to 0 is 1, and all other ak is 0, aj is 0, at t equal to 0. So, we'll plug only that on the right hand side, and we'll calculate the left hand side. The left hand side ak of t dak of dt is equal to psi k e prime, and only the summation n equal to 1 to infinity, only n equal to I will survive, others are 0. So this is only I p per e k minus e I e by h bar. This is 1 to start with. So this equation simplifies, and this equality sign is actually approximately, and this gives immediately that ak, and there is a ih bar. Yeah, there is a ih bar there, and immediately gives ak equal to 1 by ih bar integral of psi k e prime psi I, integral of these things. So integral of this thing is e to the power I ek minus ei by e by h bar minus 1 by ek minus I by h bar. So this I will give a minus one. This h bar will cancel. So basically, finally, uh, this will become aka of t approximately equal to psi k e prime psi I, these things. So we are interested in the modulus, so the modulus will be modulus of this, and if you take the modulus of this entire thing, you will get some 4 coefficient sine square ek minus ei t by 2 h bar, and that's why there is a 4 will be upstairs, and I think that should be, yeah, there will be a square ek minus ei square. And as t goes to infinity, and the idea of t goes to infinity means we are making this transition very slow. So that's the idea, t going to infinity, we're making this transition very slow. The sine square function, this function, it looks like this is sine square function, something like that. And as t becomes infinity, these functions become more sharp and sharp. And so this function goes to a delta function. So this becomes a delta function, and so this becomes this psi k e prime psi I square, uh, and a 2 pi by h bar square. This h bar square counts because there is a h bar, and delta of ek minus ei. So you will find the derivation in any good quantum mechanical textbook. But that's the idea. This is called the rate. Rate from transition from I state to k state is given by this mod of ak of t square, and this rate is 2 pi by h bar, 2 pi by h bar, not will not be h bar square, but h bar, uh, psi k e prime psi I square, uh, delta ek minus ei. And that is actually the idea behind this Fermi golden rule, that if you have any state, so these are the states. So if you have any state I and another state k, the rate of transition from going the state I to k, because of this new perturbation, new term in the potential, is given by this state. And now, how do we use this in Boltzmann transport equation? The Boltzmann transport equation, the collision is nothing but this. So I have an electron moving in this direction and gets collided by some impurity atoms. Let's say this is some impurity atoms. So the initial state psi of I was e to the power I k dot r, which is k initial. K initial is directed along this direction, and this is the final state psi final, which is e to the power I k final dot r. And what is the transition because of this impurity atom to go from the initial state to the final state? And that is this is given by this, and here you can write k as final, and there k as final is e of a, e of k b of final. So this way you can calculate, and one model of impurity is delta point defects or delta impurity. So the V of R, that I call V prime of R, is some potential V naught times delta R minus the impurity atom position. Let's call it R of J. and there are many impurity atoms. So J goes from some 1 to Ni number of impurities. So in the sample, number of impurities. So in the sample, you have many impurity atoms. So you consider this kind of a potential, and your wave functions psi initial and psi final are given by to the power I k r to the power minus I k r, and the rest of it is just doing this calculation. And also one more calculation: the impurity atom are you have to do a averaging, and averaging over the impurity position. Which means, so if you in your sample, this is your sample, if you, so this averaging should be done even if you are doing some kind of numerical calculations. Otherwise uh, there will be some problem, because you are going to get some result with specific impurity. So if you fix the position, so whatever you will get is a fixed pattern in terms of quantum mechanical effect, like interference and other things. So you cannot fix the impurity position, can fix the impurity position. So impurity position and not fix the impurity position. So what you have to do, you have to average, take the average. You have to take the average for different positions. Take average for different impurity
Last
positions.
10 minutes, ma.
Take average for the different impurity positions. So that's called impurity averaging. So impurity averaging is one thing that you have to do, and this is the Boltzmann, this is the Fermi golden rule that you use for calculating these things. Another application of Fermi golden rule is when you consider electron phonon or electron photon interaction. So another application is considering electron phonon or electron phonon or electron with photon. But there, since phonon and photon has some energy, so there the Fermi golden rule needs to be changed a little bit. And the idea to change it is start changing from here, start changing from this formula itself, and this formula is the actual formula. So you should always start doing from there, because that is the exact formula. And then from there, if you do all these steps, you will know what kind of approximation you are making. So one thing is changing v prime, and v prime of t is taken to be some f e to the power minus I omega t plus f is for some force, let's say, and f dagger, because v is an operator, f is an operator. So, and that must be Hermitian. That's why I have taken f dagger, and this v must be Hermitian. And if you take this and do these calculations again, so you will get two terms basically, because you have two terms here. So the rate will be the final rate psi k v prime of t I will have two terms. Uh, this will have two terms. This has two terms. So a of k will have two terms, and this is k f I become minus I omega t plus k f dagger I because I omega t, and then a k of t will have two terms, a k of t will be this k minus k f I e to the power minus I. So there is not only this term here, but also omega. So it will be to the power I e k minus e I minus omega t by h bar uh, plus this is I h plus similar ek minus ei plus omega t by h bar. And then this is dak dt, and when you will take the integral, that will be 1 by h bar, and it will be 1 by h bar, and one thing h bar by I coming from there, and with a minus sign. So everything cancels. So what you will have is f ki. I'm writing this f ki e to the power minus I k minus ei minus
Keep
omega
there only, ma'am. I will take.
h bar minus 1 by ek minus ei minus omega plus f dagger ki and plus sign. So one of them will remain and another one will not. That is the main point of telling it. Ek minus ei minus omega. Now, if one of them is very small, then that term will have the largest contribution. So again, one of them will remain, and that will be either e to the power ek delta. That will give either e to the power ek minus ei minus omega, either this or only exclusive or the other term will be k minus ei plus omega. So sometimes the Fermi golden rule, the rate is written in this form 2 pi by h bar uh, k at the final step b I and delta of E final minus E initial plus minus is h bar. H bar. And this is this says that the energy is conserved in the collision. So if there is one electron and there is one photon or phonon, uh, and that has h bar omega, and the energy of electron is initial, and the final energy will be E initial plus h bar omega, that is E final, and that is the absorption, and this gives the absorption process, and this gives the emission process. So emission process is exactly opposite. If this is the electron energy, electron emits a photon or phonon of h bar omega. This is the final energy EF. EF is equal to EI minus h bar omega. So this gives the emission process. And that is the conservation of energy in the absorption of the emission process. And this rate and this part gives you the amplitude or the magnitude of the ray. So this part is required. And this gives the energy conservation. And this gives the magnitude.
Hello, girls, please leave. Last 5 minutes, dears.
That is the Fermi golden rule, which is used in many places. And the last thing I just want to tell you is I think I thought I told you that I'll tell you. So uh, here, so in the Boltzmann equation, I told you that this will come in the Boltzmann equation in the quantum correction of the Spinor-Boltzmann equation. In the Boltzmann equation, this is the Boltzmann equation: del f del t plus dr dt uh, del r of f plus dt dt del p of f is equal to this collision term. And the relaxation time approximation, this is f minus f sum equilibrium by tau, the relaxation time approximation. So now there will be an additional term which is 1 by I h bar uh, f with h. This is the commutator relation. And when the commutator relation will be valid, otherwise the commutator will be zero when these are kind of matrices. And that will come in Spinor-Boltzmann equation. And the Spinor-Boltzmann equation is somewhere f is not a scalar function, has matrices, four quantities. Uh, and that comes because of the Pauli spin matrices. For Pauli spin matrices, and the Pauli spin matrices are sigma x 0 1 1 0, sigma y 0 minus I 0, sigma g is 1 0 0 minus 1, and that is because a spin state is given, has two components, spin up and spin down component A and B, and that gives a spin state. uh, and that's why the Boltzmann, in the Boltzmann transport equation, F becomes a matrix, and also H is a matrix, and one form of H is sigma dot B, where sigma is this sigma x x hat plus sigma y, sigma s I x y and g. So this x means the unit vector in the x, y, or g direction, and this sigma x x hat is the matrix. So this is a very peculiar notation. Uh, these are the matrix operator. So usually the hat in the sigma x is omitted, uh, and B is the applied magnetic field direction. If B is the applied magnetic field direction, then that will be the energy due to the magnetic field because of the magnetic moment of electron, and that will give rise to this Zeeman effect and explanation of Stern-Gerlach experiment and so on. B applied is the magnetic field. So in this case, you actually add a term which is this term, and you see that I had started with the total rate of change of DLF del T. So this part can be written down as the total so rate of, so initially this is kind of the total rate of change of del F del T is the partial change of del F del T plus 1 by I h bar F comma h, only if this is the Heisenberg equation of motion. But right now we have a distribution function. An actual way to go through is going to the quantum level equation. But again, this is the correction to the Boltzmann transport equation. This is the quantum mechanical correction to the Boltzmann transport equation. And this spin is also quantum mechanical thing. So this was, of course, was not is not any classical phenomena. So this is kind of correction to the Boltzmann transport equation, and this correction should be included whenever you are talking about any magnetic materials or magnetism or spin orbit coupling and things like that. So that there you deal with Spinor-Boltzmann equation and Spinor form of the distribution function. This is also called the Spinor distribution function. Okay, that's it. Any question? Okay.